All right, if you remember from this semester, Chapter 5, we split up into two parts, 5A and 5B. So 5A starts with number 14. Now actually 5A is what we did after doing Chapter 5B, but we'll just go in the order that we have here. So 5A starts with number 14, and it's going to end when we get to 25. So in this video, we're going to stop at that point just to cover that content that we did in that one chapter where we tested on Chapter 5A. So let's start with number 14 here. So it says use a Pythagorean identity to find sine of theta if cosine of theta is 0.45. So remember, on your cheat sheet, you could have the Pythagorean identity and all of its alternates. Well, the most basic one is that the cosine squared theta plus sine squared theta equals 1. And we're trying to find the sine of theta if we know the cosine of theta is 0.45. So we would have 0.45 squared, plus sine squared theta equals 1. So if I want to solve for sine, I would say sine squared theta equals 1 minus 0.45 squared. You can do that in two separate pieces, or if you want to do that in one step, we end up getting that the sine squared of theta equals 0.7975. So to find theta, we're going to take the square root of both sides. So when I take the square root of both sides, we're going to have two solutions, a plus and a minus. Sorry, it's not theta that we're finding, we're sine of theta. So we take the square root of both sides to get the sine of theta by itself. We get plus or minus the square root of 0.7975, which is plus or minus 0.893. So that'd be your answer for number 14. Let's look at number 15. So number 15, it says if cosine of x is negative 12/13 and x is in the second quadrant, find sine of 2x and cosine of 2x. Well, the first thing I'm going to need to do is I'm going to draw the triangle because that's going to help me out here. Now we know x equals negative 12/13 is in the second quadrant. So I'm going to draw a right triangle over here in quadrant 2 where this is the angle. Now, remember, cosine is adjacent over the hypotenuse. So that tells us this would be negative 12. Our hypotenuse would always be positive, so that's going to be 13. So the first thing I got to do is I got to figure out, well, what's this value here? So we can use the Pythagorean theorem. So it would be negative 12 squared, or 144, plus, we'll just call that a squared or b squared, whatever you want to call it, or even x squared, equals 13 squared, which is 169. And if I subtract 144 from both sides, I get a squared equals 25. Now, technically, when I take the square root of both sides, I'd have plus or minus 5. But I know over here in quadrant 2, my y value is going to be positive. So we're going to say that this is a positive 5. So now we have everything we need to find the sine of 2x and the cosine of 2x. So now the sine of 2x, remember our properties, our formulas for the double angle theorem. Sine of 2x means that we take 2 times the sine of x times the cosine of x. So we know the sine of x is going to be, again, the opposite over the hypotenuse. So the opposite of the angle is 5, and the hypotenuse is 13. The cosine of x, that's the one they gave us, is negative 12/13. Now when we go to simplify this, you could just multiply all those numerators together. So 2 times, this would be the same as 2 over 1. So 2 times 5 would be 10, times negative 12 would be negative 120. And 13 times 13 would be 169. And that can't reduce, so that would be your answer for the sine of 2x. Now the cosine of 2x, that's a little different. Cosine of 2x, remember the formula for that, that's our double angle formula. That's cosine squared x minus sine squared of x. So now let's take again what we know. We know the cosine is the negative 12/13, so we're going to square that. And sine is 5/13, and we're going to square that as well. So when I square negative 12/13, I get 144 over 169. When I square 5/13, I get 25 over 169. So when I go to simplify that, 144 minus 25 is 119 over 169. So that would be your answer for the cosine of 2x. All right, let's look at number 16. Number 16 says if the tangent of x equals 4/13, use an identity. There we go. Use an identity to find the secant of x. So slight typo there. So to find the secant of x, we first have to again look at those alternates to the Pythagorean identity. So one of those is that 1 plus tangent squared of x equals secant squared of x. Well, we know that tangent is 4/13. So we can simplify this. Now, I'm going to do a couple things here. I know when I square 4/13, that's going to be 16 over 169. And I know when I add that to 1, I'm going to have to have a common denominator. So I'm going to write that 1 as 169 over 169. So now when I add those together, I get 185 over 169. So when I take the square root of both sides, I get that the secant of x equals plus or minus the square root of 185 over 169. Now I want to simplify that because the square root of 169 would be 13. And 185, that can't be reduced at all, or that can't be simplified at all. One way to tell is, I know that 185 is divisible by 5, but 5 goes into 185 37 times, and so it can't be simplified. Because 185 would just be 5 times 37, and I can't take the square root of either of those. All right, so that's how I do number 16. All right, let's look at number 17. Find the exact value of the cosine of 105 degrees. So this is where we're going to have to use that cheer formula. So find two values from the unit circle that add up to be 105 degrees. So make sure that they're values that are on the unit circle. So don't use like 90 and 15. Because even though 90 and 15 would add up to be 105, and we know 90 on the unit circle, we don't know what 15 on the unit circle would be. So use two values that we know from the unit circle, like 60 and 45 degrees. And then we use that cheer formula. So remember, that's going to be cosine, sine, so change the sign, sine. So let's plug in our 60 degrees and 45 degrees. And let's solve each of these. So now the cosine of 60 degrees is 1/2. The cosine of 45 degrees is square root of 2 over 2. And the sine of 60 degrees would be square root of 3 over 2. And the sine of 45 degrees is also square root of 2 over 2. So when we simplify these, we'd end up square root of 2 over 4 for the first two. Second two, that's square root of 6 over 4. We can combine those to be square root of 2 minus square root of 6 all over 4. Be your answer for 17. All right, so number 18. They're asking us to simplify this. Now, if you notice, this is based on the cheer formula for the sine function, because we have sine, cosine. Oh, it doesn't quite follow the sine of the cheer formula, because it goes sine, cosine, sine, cosine. Let's actually change that around. So this would be sine, cosine, cosine, sine. So it would be the cosine of pi over 5, sine of pi over 2. Okay, so we're going to take and switch those two around. So now it's in the right form for our cheer. Sine, cosine, cosine, sine. So this is based on the sine cheer. Our values for theta would be pi over 5 and pi over 2. So let's change that so we can combine those to get a single value for theta. So you want to get a common denominator. It looks like the common denominator would be 10. So those would be 2 pi over 10 plus 5 pi over 10. So now we can combine those. So our answer would be the sine of 7 pi over 10. Your answer for number 18. Let's look at number 19. We have to simplify this. Sine of theta plus tangent of theta times the cosine of theta. Let's see what we know. Remember, the tangent of theta is the same as sine over cosine. Let's see if that helps me at all. Oh, that looks like it's going to help, because if you notice, sine over cosine times cosine, these cosines would cancel out, leaving us with sine of theta plus sine of theta. So if we have sine of theta plus sine of theta, we have two of the same, so it'd be 2 sine of theta. So that's kind of like a proof, even though it wasn't a proof because we were just simplifying, but same idea. All right, let's look at number 20. So again, the same idea as the previous one. We're not doing a proof here, but we are simplifying this. All right, so we see that we have some cosecant and a secant in there. Let's see what happens when we simplify these. By the way, this is just beta. So remember, the cosecant's the reciprocal of the sine function. The secant's the reciprocal of the cosine function. Well, how does this help me? Well, let's do this. Let's simplify this piece using keep, change, flip. So we'd keep sine of beta, keep the numerator, and flip the denominator. When I flip the denominator, sine of b over 1 is just sine over b. All right, let's do the same thing. So we plus. Let's do the same thing now for this one. We'll do keep, change, flip. Keep, change, flip. So we keep the numerator as cosine of b. Flip the denominator. Well, when we do that, that's going to be cosine of b over 1, which is just cosine of b. Well, look at what happens now. So now this will be the same as sine squared beta plus cosine squared beta. And even though it's not the right order for our Pythagorean identity is cosine squared plus sine squared. So if you want to change the order, you can. But remember, when you add, it doesn't matter. So this would just be 1. So that whole mess that we started out with in the beginning just simplifies to be just 1. All right, here we get to a proof, number 21. So remember, we're going to work on the left side. So leave the right side alone. We want to get the left side to look like the right side, though. There's a couple of different ways that you could start this one out. So maybe, I know the most common thing that people do is they, well, actually, let's do this. I was gonna do something different, but I think this would actually be easier. 1 tangent square, or 1 plus the tangent squared of x. That's one of the alternates of the Pythagorean identity. Remember, that's what secant squared is equal to. So this would be the same as 2 tangent of x over secant squared of x. Now, if you started this one by changing tangent to be sine over cosine, the denominator to be sine squared over cosine squared, you could do that. It said it requires a little bit more work, because then in the denominator you're going to have to change the 1 to be cosine squared over cosine squared. You have to add those and then do keep, change, flip. This way we could just get to this point and just, again, recognizing that 1 plus tangent squared is the same as the secant squared. So that's where using a note sheet is going to be to your advantage. You can have that on your note sheet there. All those alternates to the Pythagorean identity. All right, let's keep going from here now. So right now I recognize that tangent. Let's get this now to be in terms of sine over cosine. And our denominator, secant squared, to be the same as 1 over cosine squared. All right, let's do keep, change, flip now. I'll go up here. So if we do a keep, change, flip, we'll keep the numerator. Change it to multiplication and then multiply by cosine squared of x over 1. And now I recognize that this cosine is going to take out a cosine of the numerator, so we'd have 2 times the sine of x times the cosine of x. Well, hopefully you recognize, maybe even have it on your cheat sheet, this is your double angle formula. So 2 sine of x cosine of x is equal to sine of 2x. So we just proved it. All right, let's look at number 22, another proof. So for this one, it looks like the easiest way to do this one is just to multiply each fraction by what we have in the denominator on for the other fraction, so we can get common denominator here. So I'm going to multiply by 1 minus sine of x on the top and bottom in the numerator and denominator. And over here, we're going to multiply this fraction by what's in the other denominator, 1 plus sine of x. It's important to use parentheses, so then that way you know what to do next. So what I'm going to do in the numerator is I'm going to distribute. So when I do that, cosine of x times 1 is just cosine of x. Cosine of x times negative sine of x, we can write it like this. Doesn't matter what order you put it in. Now I could put this over a single fraction, but that would kind of defeat the whole point of doing all this work. I'm trying to get a common denominator so I can write this as a single fraction. So I know my denominator is going to be 1 minus sine of x times 1 plus sine of x. We'll simplify that in the next step. All right, let's move on to the other fraction. To get our numerator, I would distribute the cosine through. So when I do that, cosine of x times 1 is cosine of x. Cosine of x times sine of x. Now I'm going to put that in the same order as the other one, so I'm going to write that as plus sine of x cosine of x. Now watch what happens. We have a negative sine of x cosine of x and a positive sine of x cosine of x. Those would cancel out to be 0. And then we're going to be left within our numerator of just 2 cosine of x in our numerator. Our denominator, 1 minus sine of x times 1 plus sine of x, if you multiply those together, you might recognize those are conjugates. So we're going to get 1 minus sine squared of x. And 1 minus sine squared is the same as cosine squared of x. So now this cosine takes out a cosine of the denominator, so we have 2 over the cosine of x, which is equal to 2 times the secant. Because remember, the secant's reciprocal of the cosine function. So we just got that one to be proven. All right, so let's do this proof. We have sine of pi minus x. Trying to prove that equals sine of x. Now you might be stuck because what do you do with this? Distribute the sign? No, do not distribute the sign through. If you did that, that's nothing like we ever did. This we have to use the cheer. If you remember the cheer formula, so this is in that form. So it's going to be sine, cosine, cosine, sine. So remember for this, we keep the same sign. So sine, cosine, cosine, sine. Now let's go back and fill this in with our pi and our x. And now let's simplify this, because remember the sine of pi, well, that's just 0. So we have 0 times the cosine of x. So obviously that's going to be 0. And the cosine of pi, well, that's going to be negative 1 times the sine of x. So 0 times cosine of x, that's nothing. And negative times a negative is a positive. So this just simplifies to be a positive sine of x, which is what we want. So once we got started, once we knew what to do with that problem, it made it so much easier. All right, we only got 2 more problems here. Let's look at number 24. So number 24, we're going to try to solve this equation between 0 and 2 pi. Okay, so that's important. We're just going to stick between 0 and 2 pi. So we're not going to have to worry about adding 2 pi n or pi n to our solution. So we're just going to find all the values between 0 and 2 pi. So how do we do that? Well, let's start by getting this in the right form. So we want to get this equal to 0. So notice I'm working with a quadratic. So I want to get it to equal to 0 to see what I do next. So I subtract square root of 3 sine of x from both sides. Now you might be thinking, well, how do I factor this? Well, you don't have to. If you notice, remember when we're factoring, no matter what we're doing, we always want to look for a greatest common factor from the beginning. And so both of these have a sine of x in common. So I'm going to factor out a sine of x. When I do that, I'm left with 2 sine of x minus square root of 3. So if I set these equal to 0 and solve them, I have sine of x equals 0. The other one, 2 sine of x minus square root of 3 equals 0. For that, I'd have to add square root of 3 to both sides and divide by 2. Our goal is to figure out what values for x would give us these solutions of 0 and square root of 3 over 2. So the sine of x equals 0. Remember, that's going to happen at two spots, at 0 and at pi. And sine of x equaling square root of 3 over 2. That's also going to happen at two spots, at pi over 3 and at 2 pi over 3 radians. So our answers are that x would equal 0. Doesn't matter what order you put these in. 0, pi, pi over 3, and 2 pi over 3. All right, but let's look at part B. So part B, this one we just have the single term, cosine squared of x equals 4. So I'm going to do this. I'm going to do this one a little differently. I'm going to divide both sides by 8. When I divide both sides by 8, I get cosine squared of x equals 4/8, which reduces to 1/2. So now to solve for x, or solve for the cosine of x, rather, take the square root of both sides. So I get plus or minus the square root of 1/2. Now you might not recognize that on the unit circle. Well, let me do this. If I take the square root of both numerator and denominator, now the square root of 1 is just 1, but what I'm going to do is I'm going to rationalize the denominator by multiplying the top and bottom by square root of 2. So I get plus or minus square root of 2. So we're going to have two solutions there. One where the cosine of x equals square root of 2 over 2. And another one where cosine of x equals negative square root of 2 over 2. So where is the cosine of x a positive square root of 2 over 2? Well, that happens at pi over 4 radians. That also happens at 7 pi over 4 radians. So those are the two spots where the cosine of x would be a positive square root of 2 over 2. Where is it a negative square root of 2 over 2? Well, that happens at 3 pi over 4 radians and 5 pi over 4 radians. So it doesn't matter what order you put those in. Those would be your answers for letter B. Now notice the difference in the wording between 24 and 25. So 24, it says to solve it between 0 and 2 pi. This one, it says we're trying to solve it for all values. So this is where we're going to have to tack on a pi n. So you'll see how that works here in just a minute. All right, so I noticed right off the bat that this is not in the right form because here we have cosine and here we have sine. So I'm going to change that cosine squared to be 1 minus sine squared. So if I simplify this, that's going to be negative 3 sine squared of x. And then we have 1 plus 2 is 3. So if I solve this, I would subtract 3 from both sides and divide by negative 3. So if I subtract 3 and divide by negative 3, I'm going to end up with a positive 1. So if I take the square root of both sides, trying to figure out what values for x would give us a positive and a negative 1. So that happens at pi over 2 radians and 3 pi over 2 radians. Now if you remember, pi over 2 radians and 3 pi over 2 radians, they're pi units away from each other. So when we want to find all solutions, we could just say that's pi over 2 plus pi times n radians. We wouldn't need to list these out twice because if I ever put one in there for n, pi over 2 plus pi is 3 pi over 2. All right, so that's the end. I'm going to stop there with number 25 because that is where we ended at with chapter 5A.